Hi, everyone. Thanks for joining us today for this webinar conversation with Bob Metcalfe. I'm Misha St. Amand. I'm head of marketing for JuliaHub, and I'm thrilled to introduce Professor Alan Edelman, who will be hosting the conversation. Just a few quick notes. We will be taking questions for Bob. Feel free to use the Q&A function to submit those, and we'll be doing those in the second half. Professor Edelman, I'll leave things to you.
Great, thank you very much, Misha. Perhaps I'll quickly share my screen and introduce myself first quickly. Professor Alan Edelman, I'm over at MIT. I'm in the Applied Math Group and over in the Computer Science and AI Lab. I run the Julia Lab at MIT. I'm the co-founder of the Julia language and also co-founder of JuliaHub. And so this is the webpage if you'd like to go take a look at that. But today we're going to have a quick conversation with Bob Metcalfe, who I'm very excited to have learned is the winner of this year's Turing Prize. And I bet everybody knows that the Turing Prize is often thought of as the Nobel Prize in computer science, very much the highest honor that a computer scientist could ever receive. So this is a very exciting moment in time. A few quick words about Bob. I just took a quick look at his biography and noticed that the one thing we both have in common is we were both born in Brooklyn, New York. Not the same day, but both born in Brooklyn, New York. Bob got his undergraduate degree from MIT, yay, in 1969. So MIT is his alma mater. He then got a master's degree in applied mathematics from Harvard up the street in 1970, and a PhD in computer science from Harvard in 1973. He went on to work at Xerox PARC. He founded 3Com, and he's been involved with technology for quite a long time, doing many, many exciting things. And what I'm most proud of is his most recent joining of the Julia Lab. And so Bob is one of the members of the Julia Lab. And I'd like to just kind of fire away a few questions to you, Bob, if that'll be all right.
Yes, but first I wanted to point out, since you mentioned where we were born, today's my birthday.
Oh my gosh, I missed that.
Yes, I was born in Brooklyn, New York on April 7th, 1946.
I see. So I think that, maybe towards the end, we could sing a quick happy birthday or something.
Or we could ask how many of the attendees of this seminar are also born in Brooklyn.
Or how many are born on April 6th?
Yeah. 7th.
Well, happy birthday, Bob.
Isn't today the 7th?
No, today is the 6th, at least here on the East Coast.
Oh, that's funny. All right. Yeah, tomorrow is my birthday. Sorry.
Oh my gosh. Well, you've always been ahead of the game, so that works. So then if you're ready, I'm going to fire a few questions at you.
Please.
And I'd like to start at the beginning and ask you that when you think back to the time when you first became involved in technology and innovation, is there anything in particular you remember that was very important or meaningful in helping you start along the path that you have taken?
Well, my father was a gyroscope test technician for 30 years. And we built a train set in the basement on a 4x8 piece of plywood, which we painted green. And we built a control system with toggle switches, neon lights, and relays. And then in my 8th grade science class, Mr. Gozier encouraged me to build a computer. So I took the toggle switches and the neon lights and the relays and built a computer, what he called a computer, which could add any number between 1, 2, and 3 to any other number between 1, 2, and 3, and show the result between 2 and 6. And that launched me into my computer career.
Pretty tough calculations there, but
it took a while for the relays to settle down once you flip the switches.
But there's something really wonderful about like doing it with your own 2 hands, isn't there? And seeing it actually work in the end. Isn't that must have been very satisfying.
I learned a lesson there. If you want to learn something, build it.
Yeah, I wonder if enough young folks these days do that as much anymore. Let me fast forward now and talk about what the Turing Prize itself was given for, which is the development of the internet. And perhaps a lot of people would love to hear the story of how did you get there? How did you what brought you to building the internet?
Well, when I graduated from MIT in '69, the hot research topic among grad students was the ARPANET, ARPA being the Advanced Research Projects Agency of the Department of Defense. And they were building a network ostensibly to save money by sharing resources. And by sharing resources, they meant logging in through a dumb terminal to a remote host and running your application program over there instead of having ARPA buy you your own PDP-10 in which to run your code. So we set out to build the ARPANET, which is Internet 1.0, and its job was to network time-shared mini computers serving dumb terminals. But then in 1973, a year after, around the time I moved from MIT, we're working at MIT, I put MIT on the ARPANET, and then I moved to Xerox Research in Palo Alto and put Xerox on the ARPANET. But then, and this is where Ethernet starts, Xerox Computer Science Lab, Palo Alto Research Center, decided to put a computer on every desk, which it must be impossible to simulate what that was like, but it was outrageous to put a computer on every desk.
In those days, I can imagine it was unimaginable.
Well, they were noisy, they were big, they were expensive, blah, blah, blah. But we decided to do it. And it was a bitmap display, which was revolutionary, a mouse instead of arrow keys for positioning a cursor on the screen, and removable media. We had these discs that held, these were removable discs the size of a pizza. You put them in the drive, which was, we call the pizza oven. And those removable media held, hold on now, 2 megabytes of data. I mean, astronomical. And then my stroke of good luck was, since I had done the ARPANET thing and other things that allowed me, I knew how to send bits one at a time down a long wire. I was given the job of connecting these PCs, and it was a big transition for the internet. This was the beginning of the transition from dumb terminals to PCs, and Ethernet was one of the enabling technologies. Its goal was to connect all the PCs to each other and to their servers within the building, within a mile of each other. And so we designed this network. Let's see, many years go by. Anyway, we built our first network. Dave Boggs and I, may he rest in peace, but Boggs and I built the first Ethernet. It ran at 2.94 megabits per second, which doesn't sound so fast these days, but it was 10,000 times faster than the network that it replaced. Not 10%, not 100%.
Yeah, 4 zeros, I get it, right.
10,000 times faster. So in that moment, bandwidth became abundant. And that would later become handy when cat pictures became popular. You had Ethernet and related networks had enough bandwidth to actually display cat pictures. So then Dave Boggs and I then filled Xerox, the corporation in Stamford, Connecticut, Rochester, New York, Los Angeles, Palo Alto, and other places. We put Ethernets there, and we interconnected them together with an internet protocol of our own design called PUP, Park Universal Packet. So we wrapped all those Ethernets in this internet. So then there was a big inside Xerox internet, which is where we got the practice to build the real internet later, those of us at Xerox. So in 1979, I left Xerox to commercialize Ethernet and the internet protocols. And so we began shipping Ethernets, but it was hard because Ethernet was designed to network personal computers. And in 1979, there weren't any personal computers.
All mainframes.
Well, Steve Jobs had founded Apple in '76. So this was 3 years later. So there weren't very many PCs. And his PCs, Steve's PCs, were pitiful 8-bit machines that were not really capable of, they were not worthy of Ethernet. They just didn't have enough memory bandwidth to support a 10 megabit per second. The second version of Ethernet, which ultimately became an industry standard, ran at 10 megabits per second. And the Apple II couldn't digest that. So the real breakthrough was the arrival of the IBM PC in August of, when was that, 1981. And 3Com, my company, built the first Ethernet NIC, or adapter, network interface controller, for the IBM PC. It was called the EtherLink. And we first shipped it in September of 1982. And soon we were, it was a hot product. It was a breakaway product. We went public on the basis of the EtherLink in 1984. And not too long later, we were shipping millions of EtherLinks per month. Millions per month. So there's a lot of learning there. There's a big difference between building one of something and building a million of them. And one of the accomplishments of 3Com is it managed to make that transition.
I can imagine the scale was quite a challenge.
Yeah, and it's a different kind of engineer. So I am very good at building a one-off, but then the real engineers come in. They say, you're using very expensive chips here, and you're using very expensive resistors here, and we need test ports to test it on the manufacturing line. Blah blah blah.
I've heard people say that there's a big difference between building something for yourself, building something for your friends, and building something for the world.
Yep, that applied here. So we started shipping Ethernet to our customers, but our customers, they would say, what's it good for? And we'd say, everything. Ethernet can do everything. It turns out that is not a good answer for customers. Customers want to know what it's going to do for them now. And bragging about how general Ethernet was didn't work. So our first useful package was PFMTS. So we shipped a diskette with PFMTS software on it. P for print, F for file, M for mail, T for terminal, and S for basically an API. What did S stand for? Something like slots. So if you had a network of PCs, you could share a printer. And those days, I mean, the laser printer from Apple cost $7,000, not $7. So it made sense for people to use an Ethernet to share a laser writer. And IBM had shipped this massive disk, a hard disk that held 10 megabytes of data, way more than anyone could figure out how to use. So you could share one of these 10 megabyte disks among a number of attached PCs over the Ethernet. And then we started sending mail around to the desktop. And then we needed to provide terminal service for backward compatibility. So you could run I guess it's called a telnet protocol for connecting to mainframes around the old ARPANET. Is that enough?
You know, you bring back memories for myself. I was a freshman in 1980, and so I've been listening carefully to the years that you were mentioning. I was a freshman at Yale University in 1980, and I remember seeing the ARPANET, the BitNet, and thinking that how wonderful it would be if I could just magically communicate by text to people all over the world. Wouldn't it be a wonderful thing? And now that I'm inundated with email, I'm starting to rethink that a little bit. But let me point out to the audience that you can type questions and answers anytime. We'll probably take them towards the end, but if you'd like to get in early, please type your questions and answers right now. That would be just fine. Bob, my next question for you is a simple question, I think, which is, if you could do it all over again, what would you do differently?
Well, I've been talking on this topic for 50 years now. Ethernet turns 50 on May 22nd. And so I've answered that question thousands of times. And the answer is I wouldn't change a thing.
I like your answer.
It has worked out so well for me and the world. I'd be reluctant to go diddle. If you diddle with the past, that changes the present. So I don't think I would change much. I mean, one of the things I would do now to fill that in is I would have learned how to sell sooner.
Uh-huh.
I learned selling as the vice president of sales and marketing of my own tech company with a PhD from Harvard in applied mathematics. I became a salesman, and I took the company from zero to $1 million a month in revenue just before we went public. And I had to learn selling on the fly, and I wish I had learned it earlier. So, for example, prior to 3Com, IBM Corporation invited me twice and paid me $2,000 twice to come to IBM, once in New Jersey, Franklin Lakes, I think it was called, and once in North Carolina, the Research Triangle, to talk to IBM engineers about how Ethernet worked, because IBM had a competing technology they were considering entering the market with. And I spoke to these two groups and I won the argument, but I did not get the order. So in selling, you learn the difference. Since I had a 6-year head start on all those IBM engineers, I could answer any question they had. I argued them out the door, and that's where they stayed. I didn't know enough about selling to close the sale in those two cases, just as an example. So a partial answer to your question is I would have learned the basics of selling sooner. I learned them eventually. I learned them during the first couple of years of my being. And by the way, being a vice president of sales and marketing is not the same as being a salesman. That is, managing salespeople and being one is different.
Different things.
So there's a whole different set of skills there.
It's funny because I think about, teaching at MIT, and I don't know if we teach sales. I doubt it, or maybe, or at least not as part of any technical course. I don't think. And at MIT, when I think about what we do, we like to be right. But as you point out, that doesn't make you a good salesperson necessarily.
Yeah, well, you learn phrases like "we had a good meeting." We had a good meeting. Yeah, and did you get the order? Oh, or I won the argument. Well, that's an engineer. I just out-argued them. But a lot of times you're selling to engineers. Actually, it's probably better not to sell a technical product to engineers. It's better to sell it to their bosses,
I'm sure.
to the business executives, rather than, because the engineers, of course, want to build everything themselves,
And so you're
not your product.
That's right. So let me move on to another question. Of course, when I heard you were coming back and being affiliated with MIT again, I was tickled pink. Maybe I can ask you what prompted you to reestablish your affiliation with MIT?
Well, I currently have 4 separate relationships with MIT. One is I'm an alum, class of 68. I didn't get my degree till 69, but I'm a member of the class of 68. And I got 2 degrees, one in electrical engineering, which is what MIT called computer science in those days. And by the way, Harvard called computer science applied mathematics. So my PhD is actually in applied mathematics, but my thesis advisor gave me permission to call it computer science. But Harvard didn't have computer science in those days.
As a member, as being an applied mathematician, that's my affiliation at MIT myself. I almost would rather you anyway. But
anyway, so one of my relationships is I'm a loyal alum. Second is I'm a donor. I've been financially successful, and I've and I donate money to MIT. I've endowed 3 professorships already, multi-million-dollar projects. So I'm a donor. I'm a trustee. I'm a trustee emeritus life. And I've been a trustee since 92, I think. And then my 4th relationship is with you. I'm a member of your lab, the JuliaHub, which is that's because I decided that my next career, my 6th career, should be computational engineering. And you are in my book, the Center of Computational Engineering at MIT.
Certainly the Julia Lab tries to be. So I think this is a good time for you to talk about what it is that you're hoping to do with Julia. You know, what's your vision of what would success look like with the project that you've been starting?
Well, I figure that I really enjoyed computational engineering when I did it. So, for example, while I was getting my degree in industrial management from the Sloan School of Management, my advisor was J.W. Forrester, who had a system called systems dynamics, which still exists. May J rest in peace. That allowed you to write models of companies and economies and cities and so on. So I became a modeler under J. Forrester at the Sloan School, and 10 times after that, used modeling to advance my projects. And I really loved doing it. So I decided more recently that as I was deciding what my 6th career would be, that I would go back to computational engineering. And it's timely because the tools for computational engineering, including high performance computing and languages and libraries and blah, 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 this is a great time to turn the effectiveness of modeling and simulation on the world's hardest problems. So my model of what I would do next is, as a computational engineer, I would take on a series of engagements, each of which was a difficult problem that needed solving through modeling and simulation. And I've started 2 of these projects already. One I started before I knew Julia, and you've heard of Mathematica. So I'm using the Wolfram language to go back and model the Ethernet, because there was some, and you should ask me about this, there was some swags in the building of Ethernet that I'd really like to go back and see if they were reasonable swags in its construction. And then my second and much bigger project is geothermal energy. I've come to believe that harvesting the heat of the earth is going to save us. And there's a revolution coming in geothermal energy. 99% of the Earth's mass is above 1,000 degrees Celsius. And we just have to get that heat to the surface and convert it to, well, use it as heat or convert it to electricity. So I'm modeling, as my second engagement in Julia, I'm modeling a geothermal well, and how deep and how wide, and and guess what I learned? I learned as I began running the first versions of this model that you need to know thermodynamics to do a model of geothermal wells. And I looked at my transcript. I have my transcript from MIT here, and there's nothing about thermodynamics on it. So I have at the moment digressing.
Taught at MIT, and I'm sure it was taught back then too, but I guess you were busy doing other classes.
Yes, I was petitioning out of anything that wasn't digital. And that would include thermal. Hey, so I Googled up thermo and found some classes. And I started taking online classes in thermo. And the guy teaching me was Sal Khan himself of the Khan Academy, teaching me thermodynamics. I thought that was cool. Anyway.
That is pretty cool.
So I need to digress a little to learn thermo, to learn how to use Julia better, linear algebra, need to know what a Hamiltonian is again. And so I'm I've left out a key fact, which is several months ago, I came down with a bad case of COVID and then suffered for several months of long COVID.
We want you to know that we really missed you and we're glad you're doing better now.
Yeah, well, I showed up, you may recall, to begin the project, and then right after that,
I remember very well.
I disappeared.
Where's Bob? We were wondering. I would like to comment about modeling in particular, because sometimes my students, various students come up to me and say, I want to get into like whatever the big thing is right now. And of course, these days there's machine learning, ChatGPT. That seems to be the motivator for a lot of people. But what I say to students is, sure, you can get into what's the big thing now. But if you really want to do something like the best possible way, get in ahead of everybody else. And lately I've been saying that even though people have been doing this for years, I think that modeling of physical systems is really the next big hot thing. That's my prediction. We'll see if I'm right in a couple of years. But I think if COVID has taught us anything, if the climate situation has taught us anything, it's that we are all affected by the physical world more than anything. And modeling of the physical world is going to be, it just seems inevitable that that'll be the next big hot thing. And I think I just heard the CEO of NVIDIA echoing essentially a similar point. And so I think, you're right on track, Bob, with modeling of physical systems being the way to go. I'd like to share.
Can I interrupt there?
Please do.
So I started drafting my Julia code, and I saw an announcement that Stanford University was having a week-long workshop on geothermal energy and had been having this annually for 40 years. So I went to this event and I spent a week in my old stomping ground in Palo Alto and discovered that there were 100 guys who had been modeling geothermal wells for 40 years. So I have a challenge ahead of me, which is finding my niche, where in that very crowded space there's room left. Now, one more thought. My approach to modeling is slightly different in that I'm not out to optimize, I'm out to discover. That is, in the process of modeling, maybe you don't believe this, but I do. You learn more from modeling while you're building the model than you do from running it. And that has to do with the choice between discovery and optimization. And I'm interested in, because I've done it before, I have a very prominent example of a discovery that I made that made a huge difference by simulating the system. Would you like to hear that story?
I'd be happy to hear the story. And I'm going to say that I can't agree with you more that the process of building something is quite possibly as valuable as running the thing, maybe even more so on occasion. I've seen it myself. I agree with you.
Yep.
Let's hear your story.
So I was building, Dave Boggs and I were building the first Ethernet, and we wanted to use no wires. 0 wires was our goal. Wires are a problem, connectors, and so our network wasn't going to have any wires. And so I went to the University of Hawaii, where there was a packet radio network called the Aloha network. And I learned 2 things there. One is we couldn't use radio because the radios were bigger than the PCs. Our constraint was we were given a card that could hold 60 MSI chips, and Ethernet had to fit on that card. And this radio at the University of Hawaii was way bigger than that. So radio was out. And the second thing I learned was that randomized retransmissions as an access method worked. And Norm Abramson, may he rest in peace, at the University of Hawaii, modeled randomized retransmissions. That is, when you have a shared channel, the attached devices send their packets, and if they get through, fine, and if they don't get through, they choose a random number, count it down to 0, and try again. The purpose of randomization, of course, is to prevent reoccurrences of the collision. Anyway, I saw that was a great solution for us. So we were going to have one wire, which is the next step up from 0. And how are we going to take turns? How are the attached stations going to take turns? And so we adopted randomized retransmissions. But I decided before we built it, I needed to know if it would work. And Norm had a model. So I modeled his model. And I'm there typing in the simulation. And I needed a random number. I needed to put a random number into the simulation because it was randomized retransmissions. So I look at Norm's model, and Norm's model did not have the mean of the retransmission variable. That is, he had finessed it with some Poisson modeling processes. He'd managed to model his thing without actually addressing the randomization process itself. Well, I typed in a number and ran it. And then I typed in a different number and I ran it. And I realized that it mattered. The mean of the retransmission interval mattered depending on traffic level. And the original Aloha network could get at best 17% efficiency. But if you changed the mean of the retransmission interval with traffic, you could get up close to 90%, 99%, depending on packet lengths and so on. So I discovered the dependence, just the idea of the dependence on retransmission. And then, so we put in Ethernet a back-off procedure, which caused you to, it turns out that if you back off in the face of overcrowding, you can optimize. So we added a back-off algorithm. It's called binary exponential back-off. And it's, to this day, in Ethernet, in TCP/IP, and in Wi-Fi, there are back-off mechanisms that come from recognizing this general conclusion that backing off is an optimization procedure that you can do in a distributed fashion. That is, the participants can use a distributed algorithm in order to optimize their use of the channel. What did I leave out? Anything?
That's a good story. I really like the idea of the notion of writing a program for the purpose of discovery. Again, as a professor, I see classwork, I see students thinking of a computer program as a means of simply automating something, get the job done, they're in a hurry, they have to get to the next job. And probably don't often enough, maybe as often as I wish I would see, actually literally play with the software that they've just written and just just see what you can discover. I'm going to mention that I think we're going to go for, I don't know, Misha, maybe another 10 minutes. Is that okay?
I think that sounds great. Are you ready for some questions from the audience?
I want to do one quick thing, and then I've got the questions, so that's fine, Misha. But let me do one quick thing first. I want to share, Bob, the software that you started is now on a public repo, and I have it right here. So anyone can find it with Metcalfe geothermal.jl. It's on the github.com JuliaLabs website. And here's the code that you wrote. And I've already seen that somebody's already done a pull request. So you're talking about, there are all these folks at Stanford who are doing geothermal things for 40 years, and that's great. And more power to them. But let me mention that the Julia world is an incredible world of really, really smart people. And the open source, we all know what can be done with open source. And I would like to invite people listening and ultimately others who have skills in this area to see if we can take your vision of figuring out how to tap into the Earth's heat and doing something practical with it, right? And so by opening it up to the world, Bob, we have this ability of all of us trying, right? So now we have one pull request, but I would love for there to be hundreds of valuable pull requests coming, in the near future. And
well, this is potentially very embarrassing to me because I am not even a postdoc in this area, and my knowledge of Julia is elementary. Oh my goodness. You mean actual experts are going to look at my toy code here?
But those days of being embarrassed are gone. This is how it starts. This is what you do. That's another lesson I tell. Like you talk about discovery. I tell students you don't have to hide away in your room and and perfect your software before you put it out. We're all works in progress. Just throw it out there and let the world help you. And it's kind of foreign to even to many of my students. But once you do it, you realize the power of doing that, and there's no turning back. So no reason to feel embarrassed. In fact, you're really getting this going. It's a wonderful, exciting possibility.
This
And
means I have to learn GitHub.
we'll help you.
You put my code in somewhere where you can pull it, but I don't know how to pull it.
Oh, I think you could just click here and and just copy and paste. You can just download with your browser. So no worries there. You don't have to learn GitHub. You could just go to this webpage. Even just
I have to
copy and
learn
paste.
Julia. So uh,
Well,
there's a
look, you're
there's a
already an
religious
expert on
war
Julia.
going.
You're already an expert on Julia. But I mean, you wrote, this code is already there. But I think it's time to switch to the questions. So let me switch to the questions. So let me see if I can get this thing to stop.
My
Okay.
code is on the screen here in my office. How did that happen?
It's because I'm sharing my screen. So it's actually I'm doing it on my screen. So,
Cool.
I'm going to pull the plug on my phone so it doesn't bother everybody.
Oh,
Okay.
good. I put in it toy model. So I've already disclaimed it. That's great.
But it's going to become a real model in no time if my hope comes true. All right. There's this wonderful question from Rajesh Natarajan. I hope I'm not mangling the name too much. When and how did you get the idea of the Metcalfe law of networks?
Metcalfe's law.
I bet you've heard of it.
I have. I've been defending it for 50 years. So in approximately 1982, there weren't any PCs, but we were selling a network of 4 PCs, we 3Com. And so we had a kit, a starter kit. So if you had 3 IBM PCs, we would sell you 3 of our cards, cable to connect the 3 cards, and a diskette with that PFMTS software on it. So you could share a printer, share a disk, send email. And we sold a lot of these. It cost $3,000. We sold a lot of these, and the customers uniformly said, this package does exactly what you said it would do, and it's not useful. So I was head of sales and marketing at the time, and so that landed on my desk. Bob, our customers are not finding our products useful. That's a problem. So I immediately ran over to Stanford, where there were some Xerox Alto PCs that you could make slides on, and I made a 35 millimeter slide. Now this is way before PowerPoint. PowerPoint 1987. This is 1982. And so I made a slide that said the cost of a network goes linearly in the number of my cards that you buy, but the number of possible connections goes up as the square. N times n minus 1 is the number of possible connections for n stations. So assuming that a connection was valuable, I wrote that the systemic value of the network grew as the square of the number of attachments. And I made 6 copies of this 35 millimeter slide and handed it to my sales force, which had 6 people in it. And they put this slide in their carousels and began pitching customers, basically telling customers, the reason that your 3Com network is not useful is because it's not big enough. And what is the remedy to that problem? Buy more of our products, which they did. And the promise was fulfilled. So they came back and they bought some more, and we went public shortly thereafter, as I mentioned earlier. So that slide then sat around until 1995, quite a bit longer, where it was discovered by George Gilder. Now, George was one of the guys who popularized Moore's law. He's one of the things he does is popularize laws. So he took this slide and he called it Metcalfe's law. I didn't. You're not allowed to name your own law. By the way, in passing, Moore, you may know Gordon Moore died last week, which is a sad event. So for all that time, it's been Moore's law versus Metcalfe's law. And I said, no, not versus. It's Moore's law and Metcalfe's law generating computational power.
Right.
So that's Metcalfe's law. And it's one scary thing is it's recently been used as a mechanism for valuing Bitcoin. So every time Bitcoin goes up, they check to see whether it's above or below the Metcalfe value line. And this is a little scary because when it gets down, whenever it goes down, people develop a bad attitude and they blame me for Bitcoin going down. I'm not valuing Bitcoin, somebody else is. Anyway, I've been defending Metcalfe's law since 1995, I guess. No, since 1982.
There's another question about whether you have had any interactions with a particular fellow. This is from, again, I hope I don't mess up the name, Ron Ubershare. He's wondering whether you've had any interactions with Doug Engelbert from Stanford Research and NLS, and according to Ron, the mother of all demos.
In 1972, I was graduating from Harvard. That's a whole separate story, by the way, which is very bloody. And I went to Palo Alto and I interviewed with Xerox PARC and I interviewed with SRI. And I met this guy in a corner office, Doug Engelbart, and he put me to sleep. He's a visionary of the first order, but God, was he boring.
Oh, no.
So I didn't accept his job offer. Instead, I went to Xerox PARC down the street. But then I had an ongoing relationship with Doug Engelbart. I was honored to be in his presence. So we stole the mouse, which he popularized, and we Xerox, you're allowed to do this, by the way, is to copy what other people do. We copied Doug. My first assignment at PARC was the internet was making its debut at a conference in Washington, D.C. called the ICCC, the International Conference on Computer Communication. And they wanted a book. It would be like the Internet for Dummies type book. And I got the job of writing it, and I wrote it on NLS. So I went and camped out in Doug's office for a month and wrote this booklet called Scenarios for Using the ARPA Computer Network. And it was done on NLS. And that was a good way to start my work over at Xerox. Doug's main mistake, it may not be called a mistake, a misfortune, was that he was too early. And he developed all of his mechanisms on a time-shared mini computer instead of a personal computer. So what Xerox did was borrow many of his ideas, but implement them on networks of PCs instead of clunky old time-shared machines.
So, as I was thinking about your stories, and I was thinking about what you said about the Aloha Net and how much bandwidth you can get, and of course, what we can do these days. This is my phone with the Julia sticker on the back, and what we can do these days. I thought I would see if you have any. In the interest of time, I think we should just give you the one last chance to give any parting words to the listeners. Any grand advice or anything you'd like to kind of part with at all?
Yes, well, why don't I have not written my Turing lecture yet. I'm working on it. And let me share with you the content so far, which is its title so far is connectivity. And in this lecture, I will argue that connectivity is a thing. It's not only a thing, it's the thing. You mentioned earlier that you had talked with Jensen Huang of NVIDIA. What a great guy. And I talked with him and he agreed with me.
Picked up on his quote anyway, in the, online, yes.
well, he agreed with me after a while. I cornered him. That the contribution of GPUs wasn't the processors. It was how they were interconnected that mattered. And they were interconnected in such a way as to make them very good at running graphics software. So connectivity is a thing worthy of study. It has its own math, like Metcalfe's law is a connectivity, a trivial one, but a Metcalfe math thing, a connectivity math thing. So, and we have been overwhelmed by connectivity. The internet is 50 years old, 53 years old. It first began operating on October 29th, 1969, as I was graduating from MIT, Harvard. And suddenly, in 50 years flat, 2/3 of the world's population, 5 billion people, are on the internet. So we have been, my conviction is that we have been flooded by connectivity, and we don't know how to manage it yet. So we have the pathologies of connectivity. You may remember when the first big pathology of the internet was porno. And the internet was almost shut down by Congress that passed an act called the Communications Decency Act to deal with this pathology of connectivity, namely the ready availability of porno. But right after that, advertising started on the internet, and many of the intelligentsia who had built the internet were very upset that the internet was being used to carry advertising. Of course, in a very short time, the entire internet was financed by advertising. So we all learned about that pathology. But hanging over was spam. And you remember for a while, spam was the big pathology. And we've sort of dealt with that. And now there's two big ones now. One is hacking the internet, security breaches, and the other one is fake news or truth, untruth. And we're learning how to deal with those pathologies. Every technology, they say, has its benefits, but it also has its downsides, and we're dealing with them. Now, I argue the internet has been an enormous plus for humanity, the connectivity provided by the internet. And it has its pathologies, but there are no reason to shut it down, as we hear from some quarters these days.
Well,
So that's my argument, which is I share some of the techniques of connectivity. For example, do we have time? Do we have a couple minutes?
kind of running out of time, but maybe one last example, perhaps. Is that all right, Misha? Okay.
Ethernet was basically the Park Ethernet that David and I built in 73. Had three features: Gerald taps for piercing coaxial cable and thereby improving the installability of the network. Manchester encoding for turning that cable on and off so the packets could be sent down the line and collisions could be detected. And then Aloha network randomized retransmissions so the stations could take turns. Today's Ethernet doesn't have any of those three technologies in it. They've all gone away. They've all been obsoleted. So what Ethernet really did for the world is in easing the transition from dumb terminals to PCs, it brought packets to the desktop. With dumb terminals, the packets never made it to the terminal because it wouldn't know what to do with them, but PCs could process packets. So packets to the desktop, abundant bandwidth, factor of 10,000 speed up on my desk. And finally, and I haven't mentioned this yet, standardization. We Ethernet group joined the standardization effort of the internet. So Ethernet and TCP and IP and FTP and Telnet and all those standards, Ethernet, we made it part of the standard, the open standard ensemble. And that was a very powerful idea. Anyway, that's the real contribution of Ethernet in the.
Well, I think your Turing lecture is going to be phenomenal. I think connectivity, one pithy word, is going to be, I think it's going to be a terrific lecture. And you've just made it easy to bring us to the closing, because now I can thank you for connecting with us today. You just put those words right into my head. And it's been great, and we look forward to the achievements with Julia. We look forward to seeing you in the Julia Lab and seeing you over at MIT. So thanks again very much, Bob.
Thank you for inviting me. It's been good.
I don't know how in the real world I'd clap. I don't know how one does that in the virtual world, but
Oh, you have to clap up where people could see you clap.
yeah, like that. There you go. Right.
Yeah.
All right.
I thank you both for this amazing conversation, and I thank all our attendees for joining us. So thank you very much, everyone.
Okay, I'm going to hit the little red button now.
All right. Bye-bye, Bob. Thanks again.
Bye, guys.